Alright, so we're going to walk through a couple of different strategies on how to multiply radicals today, and then how to simplify some as well, where things aren't just perfect squares like we've been looking at. So you've got a couple of different strategies. If you have, you'll notice the first two problems are essentially the same. Because they are split apart so nicely, you have the option to either treat each of them separately, so the square root of 4 is 2, the square root of 25 is 5, or you can always merge them together. So the square root of 4 times 25 would be the square root of 100, which would put you in the same spot. So for me, it's going to kind of depend on the numbers. Obviously, if it weren't the square root of 4 and it was the square root of 3, we would have less options. So same thing is going to work for cube roots. The cube root of 27 is 3. The cube root of 8 is 2. This is one exact same problem I'm not even going to bother doing. You would get to 6. 27 times 8 is something. The cube root of that something is apparently 6. But to me, that is when that strategy is not going to be as useful. So the one thing that is important for radicals is that they have to have the same index. So the index is this number right here. So square roots multiply with other square roots. Cube roots will multiply with other cube roots if we are going to just make their product our new radicand, the number underneath. So being able to kind of smush those together and merge those two radicals is only possible if the indices, that's just the plural of index, are the same. We'll have some other strategies later, but for right now, being able to do things like the square root of 6 is only possible because they are both square roots. So cube roots times cube roots are just going to be cube roots of the product. So only if those indices are the same. So we can also do that with variable expressions. So we have a square root here times another square root, which means it can be the square root of the product. So the square root of a plus b times the square root of a minus b, we know, would be a squared minus b squared. Those middle terms are going to cancel out. So just a caution over here, you can tell going backwards, the square root of a squared minus b squared, it went to that, right? That's where it came from. It is not simply the square root of each part. That is different. The square root of a squared, sure, is a. The square root of b squared, sure, is b. But the square root of their difference, that is not going to be the same thing. So just something to look out for when we've got those multiple terms. So I want to walk you through two different methods. You will probably find one that you prefer. But I kind of toggle back and forth just depending on if the numbers are nice. I might use one strategy versus another. So option number 1, the square root of 20, if you can find, kind of using the opposite of that product rule, instead of merging together two radicals to get the square root of 20, if we think about breaking it back apart, the square root of 20 is the square root of 2 times the square root of 10. It's also the square root of 5 times the square root of 4. One of those is going to be better than another, and it's because we want to choose one that is a perfect square. So the square root of 4 times the square root of 2, the reason I would want to break it down that way is because the square root of 4 can be simplified. It's a perfect 2. And then that square root of 5 is not. And that's okay. That's as fully simplified as it's going to get. We worked with perfect squares a couple of days ago. Now these just aren't perfect. They're going to have some sort of number underneath your radical still in the end. So that's option number 1. If you can find a perfect square, I would love to. So the next one before we even move into the next type, this jumps out at me as a lovely problem because I can see a big perfect square in there. The square root of 200 is the same thing as the square root of 100 times 2. And then I've identified this as my perfect square. The square root of 100 is 10. So we have 10, and then we still have that square root of 2 because it's just not a perfect square. So that's option number 1. To me, that is great if you can spot those perfect squares, but it's not easy to always look at a number and be like, great, an 81 goes into there. You may not be able to see all of those perfect squares as factors. So option number 2, if you'll recall your factor tree, if I factor 20, in whatever capacity I want. Anytime you find a pair, you're essentially finding a square, right? Because squares are just a number times itself. So this number that we have paired up is going to go on the outside, essentially because it is a square. There are two of them, 2 times 2. And then the number that is left over is your 5. So same answer, just slightly different method. So the only way that's going to change is if you have a fourth root, for example. So let's continue this method with the one below. If you have a fourth root, you are looking for pairs of 4, right? Squares would be something times itself. Something to the fourth is something times itself, itself, itself. So here we would have 2, and then our leftover number is a 3. To me, like, I don't know another option you could have done for this one. You would have had to recognize 16 as a fourth root, which is a good one to know. The fourth root of 16 is that perfect 2, and then you're left with the 3. So probably, especially for 2s, it's going to be helpful to know your 2 to the second, to the third, to the fourth, to the fifth, maybe to the 6th, just knowing those powers of 2s. And a few of the 3s I think would be helpful as well. Because ideally on this next one, we would recognize that 8 is a cube root that we use quite often. So this could break down into the cube root of 8 and the cube root of 4, where then that is a perfect 2, and we're left with the cube root of 4. The square root of 18, again, you can use whichever method you want, but I recognize that as a perfect square, and then it's going to have that leftover 2. I can already see the y doesn't have anything, right? You can't take the square root of something that's not at least squared. And then the square root of x squared is x, and remember that does need absolute value bars. And this last one with variable expressions, once we take out our GCF, we recognize this as a square, x minus 1 to the second power. So square rooting that square will bring that x minus 1 to the front, but the 3 would then remain underneath that radical. All right. I'm going to encourage you at this point to maybe pause your video and see what you can do with these 5 problems. And then I'm going to go through these fairly quickly so that you can check them before we look at the very last part we need to do together. All right, so for all of those, I just made my own instructions that said assume variables are all positive. So I just ignored absolute value r's for the time being so that you could get practice with just simplifying these radicals. So the last thing I want to look at with you, and I'll pick and choose a couple of these last ones, is very similar to the product rule, where we can either break apart the square root of 20 into the square root of 5 and the square root of 4, or take the square root of 5 and the square root of 4 and make it the square root of 20, how we can go both directions. The same thing is going to be true for quotients. So you'll notice, again, it does have to have the same index, which they would if they're underneath the same radical. What you can do is essentially just separate them. So if we have square roots, for example, we can take the square root of the numerator and the square root of the denominator and just simplify them separately. So for the first one, this is just the same as the cube root of 27 and the cube root of 125, which is 3 and 5. So we end up with 3/5. So the only difference, this one is going to be perfect. Again, I'm assuming all variables are positive at this point. If you have leftovers, right, if you don't have a perfect square, that's okay. It stays either in the numerator or the denominator. So the square root of 16 is 4. The square root of x to the third is x, but there's going to be one left over. If we think about, we have one pair of x's, but one left over. And that's fine. All right, I'm going to let you try this next one, or pause something, and then check. So taking something that is where there is a fraction underneath the radical, same is going to be true where if they are separate, we can merge them. So if you have the square root of 80 divided by the square root of 5, you can make it the square root of 80 divided by 5. The square root of 80 divided by 5, let's see, 80 divided by 5 is 16. And then we could keep going. So that's option 1. That is obviously really useful if they divide nicely, right? Had the denominator been a 7, we would have had to look at some other strategies. But option number 2 is you can actually simplify first. So the square root of 80, just take my word for it for now, is 4 times the square root of 5. Then, because we have the same thing in both the numerator and the denominator, we can divide and we end up in the same spot. So again, that strategy is only great if we have the exact same thing. If I had ended up with a square root of 5 and the square root of 2, we would need some more strategies. So the next one, again, if I'm just kind of combining this into one fraction, 32 divided by 2 is 16. Cube root of 8 and the cube root of 2. The cube root of 8 is 2. Whoops. And so we end up with 10 times the cube root of 2. All right, I'm going to let you pause and again try those last two and then check these before you finish.